Okay, this is IGCSE Physics, um, 062542, and October, November 2020, questions 4 and 5. Okay, the voltmeter here we have a thermometer. The voltmeter reading is 5.4 millivolts. State the name of this type of thermometer. What type of thermometer has two junctions with the same material on both and a different material on the other, and the voltmeter or galvanometer? We know this is called the thermocouple. It's a nice mark. Okay, figure 4.2 shows the same thermometer used to measure the temperature of liquid X. With the setup in figure 4.2, the voltmeter reading is 1.7 millivolts. Calculate the temperature of liquid X measured by the thermometer. Take this as a formula. Delta T1 over V1 is equal to delta T2 over V2. Okay? What does this mean? The change in temperature over here, how much was it? 100 minus 0, right? 100 minus 0. And how much was the reading? 5.4, right? It should be equal to delta T2. Delta T2, it's final minus initial, right? We don't know how much the final temperature is. So we're just going to call it temperature final, TF, minus the initial temperature, 20, over V2, which is 1.7. Let's solve this. You're going to get 1.7 times 100, it's 170, is equal to 5.4 TF minus 20. Okay, if you divide by 5.4 on both sides, 170 divided by 5.4, you're going to get this. And then you need to obviously take the minus 20 to the other side, is going to become plus 20. So you're going to get TF is equal to, should be to two significant figures, 51 degrees Celsius. Okay. Or, you know what? Just to show your work and make it a bit nicer, put 51.481 dot 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 dot, which is 51 degrees Celsius to 2 SF. Okay. Let's check the marking scheme. 51 degrees Celsius. Okay. Suggest an application for which this type of thermometer is more suitable than a liquid in glass thermometer. When would you rather a thermocouple than a liquid in glass thermometer? We said thermocouples can measure anything with a high temperature. مثلا, the liquid in glass thermometer can maybe reach 150 degrees maximum, but the thermocouple can go up to 700, 800 degrees. Okay, with anything with high temperatures. Let's check the marking scheme. Any application involving higher temperatures or rapidly changing temperatures, or anything that has to do with the properties of the thermocouple, which are all correct. We also have question 5. Specific latent heat. You guys know that the latent heat has LF and LV. Latent heat of fusion is the amount of energy needed. Remember, LF is equal to M. Sorry, no. The energy needed, LF is equal to Q over M. It's the energy needed per 1 kilogram, energy needed to change state of 1 kilogram. And LV is also Q over M. But what's the difference between these two? LF is needed to change it from solid to liquid, and then from LV is from liquid to gas. But in this case, they're not saying LF or LV, they're saying in general latent heat. Latent heat is always to change state. So, specific latent heat is the energy required to change the state of 1 kilogram of a material. Okay, let's check the marking scheme. They said thermal energy need to change state of 1 kilogram of material. Explain the melting of a solid in terms of molecules and energy. Whenever, I'm going to give you a trick. Whenever you say in terms of, that means, and it's 2 marks, so that means there's 1 mark for explaining the molecules and 1 mark for explaining the energy. Okay? What happens to molecules when you melt? Okay? When you're a solid, the molecules are tightly packed, right? They kind of look something like this, right? Over here, and then so on and so forth, and they form whatever, a solid. Molecules are tightly packed. How about a liquid? They're sliding across each other, right? So, to go from a solid to liquid, the bonds between molecules of a solid must be broken. And what does this have to do with energy, guys? To break bonds, you need energy. So the bonds between molecules of solid must be broken, and this requires the input of energy. So if you check the marking scheme over here, molecules must be separated or the bonds between them must be broken. And the second mark is the work done or whatever energy is required. Okay. You're not allowed to say increase of kinetic energy because, guys, we're talking about the solid here. We're not really talking about gas. The gas law of where temperature increases, kinetic energy increases, that's for gases, guys, not for solids and liquids. Okay. B. An electrical heater is used to heat a liquid to its boiling point. Figure 5.1 shows the apparatus. When the liquid is boiling, the heater supplies 1.26 megajoules of thermal energy. The mass reading decreases from 3800 to 2300. Calculate the specific latent heat of vaporization of the liquid. So, it's very, very easy. You guys know Q is actually equal to mLV, right? And therefore, some people also memorize it as LV is equal to Q over M, which also works. How much energy am I using? 1.26 megajoules. Remember that mega is 10 to the power 6. What's the mass? Please don't put 3800 or 2300. The mass is how much liquid vaporized, how much liquid left, right? Okay, how much liquid left? How much vapor left because we're vaporizing it. From 2800 to 2300, it's how much? 3800 minus 2300, let's just say over m. And the mass is equal to 3800 minus 2300, which is equal to 1500 grams. But remember, we're not allowed to keep it as grams, which is equal to 1.5 kg. So now we can find our LV. It's just 1.26 times 10 to the power of 6 over 1.5. And let's do this on our calculator. 1.26 times 10 to the power of 6 over 1.5. You get 840,000. To scientific notation, we're gonna put this in scientific notation. It's 8.4. It needs 3 significant figures, so we'll use. I should have put 1.50 here. Okay, I'll use 3 significant figures. So 8.40 times 10 to the power of 5. Okay, so 8.40 times 10 to the power of 5. And remember, it's unitless, right? No, it's not unitless. You're dividing energy by mass. You're dividing joules by kilograms. So the unit of latent heat is joules per kilograms, as well as the unit of the specific heat capacity is also joules per kilograms degrees Celsius. Okay, because in Q is equal to mc delta T. C is equal to Q over m delta T. So joules divided by kilogram degrees Celsius, right? So you could either say C's unit is actually joule kilogram minus 1 degrees Celsius minus 1. You can, many people, they write in different ways. I like to use this. It's easier for me. Anyway, let me continue. In the marking scheme, they actually put it as 8.4 times 10 to the power of 5. I'm pretty sure there's no, like, it's fine if you keep it as 8.40. There's no, because I can't really see, it should be 3 significant figures. I guess it's fine to keep it as 8.40 or 8.4. They didn't say strictly 8.4. Yeah. Okay. State and explain a precaution to improve the accuracy of the value of specific latent heat calculated in B. Remember, it said state and explain. So 1 mark for stating, 1 mark for explaining. Okay. In the actual experiment in the physics book, they actually mentioned that it's the container is wrapped with any insulator. Okay, that obviously doesn't melt. An insulate, like an actual proper insulator that doesn't melt, like rubber or whatever. Why do we do this? It's because the external temperature should not play a role in changing the temperature of the liquid. So we're gonna say what the container must be enclosed or not enclosed, must be wrapped with insulator. And why? Because it minimizes, right? It minimizes the influence of external temperatures, right? External temperatures. Let's check the marking scheme. Apply insulation, whatever, and this reduction of thermal energy slash heat losses. So it minimizes the influence of external temperatures, just to be safe, which reduces heat loss. Okay, reduces heat loss. That's your keyword here. Okay. نحن we're done here. Thank you so much for watching. Good luck.